we're going to talk a little bit about how you characterize laser beams. Specifically, we'll talk about Gaussian laser beams. Most lasers have a Gaussian intensity profile, so we'll describe what that means, why that's important, how we can understand how that profile will propagate, and then how we measure it and how we understand beams that aren't fully Gaussian. Okay, so laser beam propagation is important. Pretty much any optics experiment you do, you're going to start with wanting to understand the output of your laser so you can understand how the beam will propagate through your experiment. And if you just imagine a typical laser, sort of the novice idea of how that beam behaves is that it's this pencil of light that propagates unchanging through space. But that is actually not the case. Like any optical field, it's subject to diffraction. And so the fact that the beam is confined to this pencil-like geometry means that it must be spreading out due to diffraction, such that in the far field, it's actually much larger than it is typically in the near field. So just to understand what we mean by the intensity profile, imagine you've got a laser beam and you insert a card into the path of the beam, and then you plot out the intensity as a function of position on that card. That's essentially what's shown here. And a Gaussian profile is one where the intensity is the maximum on axis and decays as e to the minus r squared as you get further away. So that's what a Gaussian beam is. The term Gaussian comes from the fact that the e to the minus r squared function is known as a Gaussian function. And we normalize that distance with respect to w, what we call the Gaussian beam radius. It's some parameter that defines how big that beam is. And so at any given plane of propagation, the profile will look like this. But if we look at how the light changes as it propagates, so here the horizontal axis represents the distance away from the laser, we can imagine a beam that is converging, so that the beam is getting smaller and smaller up until it gets to some point that we call the waist, where its width is minimum. That's identified by W0 on this graph. And then from that point on, as it propagates, it begins to expand due to diffraction. So time reversal symmetry tells us this is a symmetric picture. And we can look at this picture and basically break it into two zones. One zone is where the beam is converging or expanding rapidly. We call that the far field. And the other zone is where it's near the waist. We call that the near field. So although it's somewhat subtle where the distinction between these zones lie, the general rule of thumb that we use to describe when we're in the near field and when we're in the far field is comparing the position to the Rayleigh range. If we're within one Rayleigh range of the waist, we typically say we're in the near field. Beyond that, we say we're in the far field. So the Rayleigh range, denoted z sub r here, is the distance that a beam has to propagate before its area doubles. And that means in any given direction, its waist or its radius will increase by square root of 2, so that the area increases by a factor of 2. For a Gaussian beam, that particular distance, z sub r, is pi times the radius at the waist squared divided by the wavelength. That's a very useful formula and one that you should commit to memory, or at least be familiar with where to look it up, as you will likely be using this one quite a bit, both when laying out optics experiments and analyzing and writing up your experiments. Okay, so if we look at this plot in a little more detail, we can say a little bit about what the beam is doing at various points. At the waist, we expect the phase fronts, or the wave fronts of the light, that's the surfaces of constant electric field phase, to be flat just due to symmetry. And so a flat wavefront means the radius of curvature of the wavefront is infinite at that point. It's useful to note that when you get out to one Rayleigh length away, the radius of curvature is equal to the Rayleigh range. And in the far field, when you're beyond a Rayleigh range away, the radius of curvature is approximately equal to the distance away from the waist. So those are a couple useful relationships. Other parameters you may hear spoken of are the depth of focus. That's the range, the distance over which the beam can be considered collimated. So that's basically from the length of the near field, from -1 Rayleigh range to +1 Rayleigh range. So the depth of focus is 2 Rayleigh ranges, or 2 pi w squared over lambda. Now, in order to mathematically deal with these changing shaped beams, we define something called the Gaussian Q parameter. So we actually define its inverse here, 1 over Q, and it has a real part that depends on the radius of curvature of the wavefronts, and it has an imaginary part that depends on the radius of the beam. Both those things change with position away from the laser, so the Q parameter itself changes as the light propagates. We'll find that there are rules for how that Q parameter changes, and through this first relation on this slide, we can relate that back to the radius of curvature of the wavefronts and the size of the beam as it propagates along. So just to understand a little bit why we have this complex quantity and why it's defined this way, if you describe the electric field in a plane, a distance z away from the laser, you can say that the electric field can be described by e to the minus I k r squared over 2q. So looking at the functional form here, what we see is that when we plug in 1 over q, the real part of 1 over q gives rise to an oscillation, basically a changing phase for the electric field as we move away from the optical axis, as we move away from r equals 0. The imaginary part of 1 over q, the I in the imaginary part, combines with the I in this functional form of the second equation to produce a negative sign, and we get an e to the minus something. That's an exponential decay. It's an e to the minus r squared over w squared. It's an exponential decay that's responsible for the Gaussian beam profile at a particular plane. So knowing the Q factor lets us write the electric field, both its amplitude and its phase. And knowing the Q parameter lets us extract the radius of curvature of the wavefronts and the Gaussian beam radius at any point, z, as described by these last two equations. Now, we can very quickly determine what the Q parameter is for a beam if we can locate the beam's waist. So at the beam's waist, we said the radius of curvature was infinite. So the first term, the 1 over r term, in our definition for Q of z, that term goes to 0. And so our Q parameter becomes entirely imaginary. And in order to know what the Q parameter is, we simply need to know the wavelength and the radius of the beam at the waist. That's W naught. If we can measure these things, then we'll know the Q parameter at the waist, and we can use these expressions at the bottom that describe how the beam size, the radius W, and the radius of curvature of the wavefronts, capital R, how those things vary with position. So basically, knowing the size of the beam at the waist allows us to understand its size and radius of curvature of the wavefronts everywhere. And the way we do that is by measuring the size of the Gaussian beam, so the Gaussian beam radius, at several points, at several different distances away from the laser. We need at least 3 points, but the more points we have, the better we can fit our data to a model. And so this graph here shows measured data points for a Gaussian beam radius at various positions away from a laser. We can see that this beam was converging as it approaches position 0, and then diverges shortly after that. And from those points, we can do a mathematical curve fit of our expression on the previous page for W of z. And that curve fit has this, it sort of looks parabolic. It's not actually a parabola, but it has the functional form shown in the expression on the right. And we can do a best fit analysis to determine the unknown parameters. Typically, those unknown parameters are the size of the waist and the position of the waist. although it would also be possible to fit the wavelength of light into this as well. So how do we go about measuring the size of the beam at a particular location? So there's a couple different ways that you can go about it, but imagine this picture on the bottom left represents the Gaussian intensity profile of our laser beam in a transverse plane. One way to measure how that intensity changes as a function of radial position is to take a pinhole and scan it across a chord of this profile, or even better, across the diameter of the profile. And that's what's shown in this bottom middle picture. If we take a pinhole and we scan it across, the power transmitted through the pinhole is the area of the pinhole times the irradiance of the beam at the center of the pinhole. So by putting a large photodetector behind the pinhole, as we scan it across the beam, we're only transmitting light from a particular point on the profile and detecting how much power is in that. And as we scan across and plot out the power, we get this Gaussian profile here, which represents the Gaussian profile of our beam. We can then measure the 1/e² points on this profile and recognize those as the Gaussian radius. It's also possible to measure the full width half max and relate that to the Gaussian radius, although those are two different things, so we have to be a little careful that we multiply by the appropriate scaling factor if we do it that way. Now, using a pinhole has a disadvantage. It has a disadvantage compared to the next method I'll describe, that if the pinhole is not infinitesimally small, then if the intensity profile is changing over the diameter of the pinhole, then our assumption that the power detected is the intensity at the center of the pinhole times its area begins to falter. And in particular, if the pinhole diameter is comparable to the size of the beam, then we will introduce a significant amount of error into our measurement. An alternative method is to scan a razor blade across the beam so that, as shown in the bottom right, you're blocking all points beyond a certain line from reaching the photodetector that is placed after the razor. And so as you move the razor out so that if it was initially completely blocking the laser, you pull it out. As you do, you allow more and more power to transmit through to the detector. And plotting that power that gets transmitted through, you get this this curve shown in the bottom right, which is has the functional form of a complex error function. Basically, the derivative of that curve is what we had in the previous plot, where we used a pinhole. The derivative of that is how much additional power gets put onto the detector by moving the razor blade a slight amount. That additional amount is just the intensity at that point times the area uncovered as you move the laser by a differential amount. So by taking the derivative of this curve, we get an expression, or we get a function that has the same shape as the Gaussian intensity profile. And unlike the calculation or the measurement done with a pinhole, this technique doesn't produce any error due to the finite size of a pinhole that we're using. So those are a couple different methods that can be used to measure the cross-sectional beam profile of a laser beam. And as we were scanning these in one direction, it's worth noting that the beam profile may not be round, so it's often necessary to scan in two orthogonal directions in order to get an X and a Y beam profile.